Welcome to the Intermediate Counting and Probability class. My name is Mr. Goobles. You can also call me just Austin. So a brief overview of this course. It'll be Monday through Friday, every day, for 3 weeks, and we'll meet at Gear Library from 2:30 to 4:30 p.m. So starting Wednesday after the holidays, we will begin to meet in person at Gear Library. And as far as what to bring, just make sure to bring something to write with, a notebook, and if you want to bring loose leaf paper or something, that'll be good too, because you will have some homework. So you'll have to write your homework on paper and turn it in. And also a folder would be super helpful. So please make sure you bring a folder and a notebook to take notes in and work through problems, and then of course something to write with. So this class is going to be all about combinatorics and probability. So every single problem that we do in this class will be related to one of those two topics, or both. And this course is geared towards problem solving. We'll learn a lot of theory as well, but problem solving will be the focus. So we'll solve a ton of problems, and we'll make sure to assign a lot of problems for homework as well. Now, the homework will range in difficulty from easier problems to really, really hard problems, and it's okay if you can't solve all the problems every day. Just do the best you can each day. I definitely expect that you read through and try every problem and think about it a little bit, but especially for some of the harder ones, you don't have to make sure that you figure out a way to solve it before class time if it's taking that much stress for you. So just know that it's normal to not be able to solve all the problems. Don't worry. And of course, ask questions, and you can bring your questions to class the next day. So don't worry, don't ever worry about that. Just work through as much as you can and get as much as you can out of this course. So over here on the right, I have an overview of all of the topics that we'll be covering. So today we're going to review all of the basic concepts of combinatorics and probability. Now, counting is a synonym for combinatorics, and combinatorics just means basically it's the art of counting things. So when a question asks you how many of this or how many ways can you do X, that's combinatorics. So we're going to review all of the basics today. Things you've probably seen before, methods you may have seen before, but we're going to review them. And on Tuesday, we'll talk about sets and logic. And tomorrow is going to be important because we will have some proof-based questions. You won't have to write, if you haven't written proofs before, it's fine. You just need to, it's the same as justify or explain. We'll prove some things, and the set theory and logic of tomorrow will help with that a little bit. And so we're going to cover some basic tools of logic and some basic vocabulary about sets so that you're able to understand that, because we'll actually need it for a lot of the concepts later on. And then Wednesday will be a super big topic, the principle of inclusion and exclusion. It's super, super important. On Thursday, we'll talk about constructive counting and one-to-one correspondences. You may also know that as a bijection, if you know that word. If you have two functions and you can create a one-to-one and onto function, it's called a bijection, and you can say that they're in one-to-one correspondence. On Friday, we'll talk about the pigeonhole principle, and then we'll have a slightly larger set of problems to do on Friday because you have a weekend to do it. And then week 2 will start, and we'll talk about constructive expectation on Monday. We'll talk about distributions. And then on Wednesday, we'll talk about a method of proof called the principle of mathematical induction. And we will prove some really interesting results using mathematical induction. And the reason we're including this in the curriculum is because mathematical induction as a method of proof it shows up all the time in combinatorics. And then on Thursday, we'll talk about Fibonacci numbers. But not only, I mean, of course, you may have heard about Fibonacci numbers before, but we're also going to learn about how to figure out a formula for it, and we're going to be talking about some interesting problems that use Fibonacci numbers. And then on the Friday, we'll talk about recursion and something called Catalan numbers. So Catalan numbers, they're kind of like Fibonacci numbers in that you can start a sequence, and in that sequence are the Catalan numbers, and they're extremely useful for problems. So we'll talk about that. And then week 3 will be a little bit harder. On Monday, we'll talk about a super important probability concept called conditional probability. On Tuesday, we'll talk about some combinatorial identities. Those are just equations or formulas that have to do with combinations, so like n choose k, formulas involving those. Wednesday, we'll talk about events with states. On Thursday, we'll talk about generating functions, which are really, 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 really cool. They show up in all different areas of mathematics, but we'll start with some basic generating functions and how to use them to solve really interesting problems. A generating function is basically, it's a function or a polynomial where the coefficients end up being the important part of the polynomial. And sometimes we'll work with infinite polynomials and multiplying infinite polynomials together, where we only care about the coefficient of, say, the x to the 33rd term or something like that. And then on Friday, we'll talk about graph theory. Now, graph theory is its own field of mathematics, so we'll get a start into graph theory, and it's super important because it's really closely related to combinatorics and probability. A graph is just a set of vertices with edges, and we'll delve into the theory of that and some interesting problems we can solve about graph theory. So yeah, that's an overview of what we'll talk about. Okay, so now let's take a few minutes just to solve these first few problems. Try your best. They're fairly basic, but we'll talk about and review how to solve these kinds of problems. And of course, for any of these problems, if you'd like more examples of similar problems, you can always ask me and I'll supply you with them. So, yep, we'll reconvene in maybe 5 minutes or so after you've had a chance to solve. Okay, so hopefully you've had a chance to solve those problems. For the first one, we have 25 choices for the first ball, and after the first ball is drawn and discarded, we can't use that one anymore, so we have 24 left. So there's 24 choices for the second, and similarly there's 23 choices for the third ball, and 22 choices for the fourth ball, because after we select a ball, we can no longer use it. So the number of winning combinations is just going to be 25 times 24 times 23 times 22. And if you compute that, you get that 6-digit number there. And for part B, you have 25 choices for each of the 4 balls, but since when each ball is drawn, all 25 balls are still in the bin. In other words, you put the ball back, there ends up being 25 times 25 times 25 times 25, or 25 to the 4th winning combinations. And notice how that's bigger than the other number. Okay, so just as a quick concept review in those last problems, if you have multiple stages in an event, you're going to multiply the number of choices at each stage to get the total number of choices. So notice how in the last problem with the balls, we had to multiply the number of choices at each stage to get the total number. And it's really important to distinguish without replacement and selecting with replacement. When choosing k terms in order from a group of n, with replacement, we have n to the k power choices. And hopefully that makes sense because we're just multiplying n by itself k different times. And then when we're choosing k items in order from a group of n without replacement, now this means we don't put it back, we can't use it anymore. Since we have n choices to choose from and we have k slots, we're just going to do n, and then we've already used one, so then times n minus 1. We've already used 2 of them, now n minus 2, and so on until we get to n minus k plus 1. Now it's super important to realize that last factor in the product there, that's actually n minus quantity k minus 1. So we're subtracting off from n k minus 1. So if you look at that, it's basically n minus 0 times n minus 1 times n minus 2 all the way up to n minus quantity k minus 1. So that's k different factors. So we can confirm that we do in fact have k choices being made here. So when order matters, and this expression in the middle of the page right here, that's an example of when order matters. This is called a permutation. So whenever you're ordering a set of things, and the order matters, and you're asking how many orders are there, that's called a permutation. So a permutation is one of those orderings. So when you ask something like what's the number of permutations, you're asking how many orderings are there. So if we start with n items and we want to know what's the number of permutations of k items, so we're asking how many orderings that have k items in them. So think of like a row of k things, but the big box of things has n things in it. There's 2 ways that it's normally also written down, and it's p of n comma k or npk, like that. Those are just other ways of saying permutation. So let's try this next problem. Here is basically the way to do it. So for number 2, we can do different cases. So we know that it has to be 3 letters or less. So that means we can either have 1 letter, 2 letters, or 3 letters. So we're going to just do each case. So for 1 letter, obviously there's going to be 5 words for that. For 2 letters, we need to form a 2-letter word. So we have 5 choices for our first letter and 5 choices for our second letter. And it's okay to use the same letter for both the first and the second letter. So it's just 5 times 5, which is 25. And case 3, 3-letter words, that's going to be 5 times 5 times 5. And therefore we get the total possibilities. We have to add the possibilities for 1 letter, 2 letters, and 3 letters. Therefore, we'll get... Oh, we won't get 125. Sorry. I mistyped that. That is supposed to be 155. So we're going to get 5 plus 25 plus 125, which is 155. And there's a word that describes just the general technique of breaking up the possibilities into 2 or more categories. It's called casework. So we can then add the possibilities of the various cases to get the total number of possibilities. So to get our answer, we'll just add the numbers we get from each of the cases. But the only thing to keep in mind with casework is that each of the cases must be mutually exclusive, meaning that they cannot overlap. There can't be a possibility that belongs to both cases that could be talked about by both of those cases. When you have several cases that you want to do and you want to add up the possibilities, all three of those cases, they have to not have anything to do with each other, meaning that there can't be a possibility that would fall under more than one of those cases. And of course, you want to make sure you have all the cases. Okay. So when you're doing casework, make sure to not do any overcounting. So the cases have to be completely different. Okay, let's take a few moments to work on these problems right here, and then we'll talk about the general methods that are used to solve them. Again, these are pretty basic, but just give them a shot. All right, hopefully you had a chance to do that. The first one can be done by casework. The first one, the first case, I mean, we have 3-digit numbers with a 0 as the middle digit. Okay, so we know that the middle digit's 0. We just have to figure out first and third digits. Well, there's 9 choices for the first digit, and there's 9 choices for the last digit, because either of them cannot be 0, but they can be any other number, 1 through 9. So that's 9 times 9, so we get 81. And for case 2, we have 3-digit numbers with 0 as the final digit. Now there's 9 choices for the first digit and 9 choices for the second digit, again because they can be 1 through 9. So we get a total of 81 numbers in that case as well. So we just add them up. 81 plus 81 is 162. Yeah. Just for your general knowledge, there's another way to do this problem, and the concept behind it is called constructive counting. So even though this problem is not very hard at all, let's just talk about the concept of constructive counting a little bit. Constructive counting is just thinking about the steps necessary to construct such a 3-digit number, and we're going to count the number of choices that we have at each step. So we usually want to start by dealing with the most severe restriction in the construction. So the most restrictive thing about the number or about the thing we're trying to count. So for example, in this problem, there's really only one restriction, but in problems in the future we'll have many more restrictions. So that restriction is that the number must have exactly 1 0, not less than 0, not less than 1, and not more than 1. It has to have exactly 1 0. So when attempting to construct such a 3-digit number, our first choice should be, well, where do we put the 0? So we know that we want to count the number of 3-digit numbers that have exactly 1 0. If we imagine such a number, we have to ask ourselves, well, where is that 0 going to be? There's exactly one of them, and there's only 3 places the 0 can be. So that kind of brings a light bulb into our head. Okay, so there's 3 different places we can put them. We can either put the 0 in the middle, or we can put it on the right. We actually cannot put it on the left. We have to rule that out because 3-digit numbers, the hundreds digit has to be at least 1, so that's ruled out. So if the 0 is in the middle, we'll count that case, and then if the 0 is on the right, we'll count that case. So if the 0 is in the middle, the other 2 digits, both of them can be 1 through 9, so we get 81. And then if the 0 is on the right, then the hundreds digit and the tens digit, both of those can be 1 through 9. So that's 9 times 9, 81 combinations as well. So again, this general idea is called constructive counting. We just got to think about, okay, well, let's imagine we have such an item. We're asking how many of them are there? Well, if I have such an item, how might I construct it? What are the restrictions on this item that I want? And it's a general good idea to deal with the hardest restriction first. And considering either if it's only one restriction, doing that one first, or if it's a hard one, if there's a mixture of restrictions, doing the most extreme one first. Okay, so the next one, let's think of the best way to approach this problem with Ali and Brenda. The best approach for this is to use something called complementary counting. So we're asked about how many ways that we can have a 3-person committee where one of them is president, one's VP, and one's treasurer. But we have this restriction. We want all of the committees of 3, where one of them's president, one's VP, and one's treasurer, where Ali and Brenda are not together in there. So if you think about it, it's a little bit easier to count the number where they're both actually in there, and then we can just subtract off. So we're going to do a kind of overcounting. We're going to just forget about the restriction of Ali and Brenda, and let's just see. Okay, so we have 20 people. There's 20 choices for president. Okay, great. We've picked the president. Now there's 19 people left to consider for VP. All right, so there's 20 times 19. And then finally there's going to be 18 choices for treasurer. So that's going to be the overcounting that we did. We counted all possible ways, and now we're going to subtract off cases where Ali and Brenda are both, they both have a title. So for Ali, we can just pick an office for Ali. There's 3 of them, and then we multiply by how many choices left there is to put Brenda in. There's 2, so 3 times 2 is 6. So there's 6 ways to have both Brenda and Ali either taking up 2 of the offices together. And now for the 3rd office, whatever it is, there are 18 people left to consider for that office. So we'll just take our 6 times our 18. And that'll give us the total number, the 3 times 2 times 18. That'll give us the total number of ways to pick president, VP, and treasurer, such that Ali and Brenda are in 2 of those offices. So remember the question asked for the complement of that. So we'll take the total possibilities, right, the 20 times 19 times 18, and we'll subtract off the complement of what we wanted to compute in the first place. So if we do that, we can either multiply out first and then subtract, or we can factor something out and multiply by the common factor of 18, whichever way tends to be slicker. Okay, so for the next one, for number 6, the answer is not simply 4 factorial because there's 4 letters. Even though there's 4 letters and we have to place all 4 of the letters in either first place, second place, third place, or fourth place, it's not going to be 24. So that's a bogus solution. If the 2 L's in ball, if they were different letters, if there was, for instance, an L1 and an L2, then it would be 24. So if we pretend that the 2 L's are different, call them L1 and L2, and that way there's 4 factorial ways to arrange the letters to form a word. But if we take any arrangement of that, like for instance, maybe we take A, L1, B, L2. So let's say we take that arrangement and we just switch the L1 and the L2. That's counted as 2 different arrangements if L1 and L2 are different like that. But if we drop the subscripts, if we just think about, oh, now there's 2 L's, then those 2 are the same. So we actually have to end up dividing by 2 because we overcounted with our 24. So the problem deals with the case of dropping the subscripts. So if we imagine that the 2 L's are actually different, then we'll have 24, but we'll divide out the repeats. We'll divide out by the overcounting that we did. So we'll take 24 divided by 2 to get 12. Now this is a super common math counts problem, so be sure that you know how to do this. This comes up on the AMC, it comes up in math counts, it comes up in all different sorts of competitions. So tomorrow we'll actually have a short little quiz. I mean, you won't be graded on the quiz because it's on YouTube, so there's really no grading there. You'll just try the problems, but we will just do several problems that are harder, but that have these concepts we'll do tomorrow. Okay, so for the sitting around a circle problem, there's 6 people sitting around a circle. We want to know what are the total number of ways to seat those 6 people such that everyone has the same, like if everyone has the same neighbors, then those 2 arrangements are considered the same. That just means if you seat people down and then you rotate the table, then those aren't considered any different. We're not going to count those. Now, the way to think about this problem is we're going to have a sort of strategic overcounting here. And which the concept below says count outcomes with symmetry. This usually means we're going to have some sort of strategic overcounting. So if there's some sort of symmetry in the problem, we're going to have some sort of strategy that we're going to use for overcounting. And really what we're going to do here is the symmetry is that you have a rotation of rotating one person, like if you rotate so that one person moves one seat, you can do that Uh, you can do it. You can not do it. You can do it once, twice, 3 times, 4 times, or 5 times. So those are 6 different possible rotations you can do. And so for every possible way of having neighbors, right, there are 6 ways that you can sit at the table. So if you've already determined beforehand who you're definitely going to sit by, then there's 6 ways that you can all sit down on the table. If we imagine all the 6 people sitting in a row, obviously there's going to be 6 factorial arrangements, but this is clearly an overcounting since several different row arrangements correspond to the same round table arrangement. And the correspondence is exactly in proportion of 6 to 1, right? Because suppose we take a row of 6 people and sit them at the round table by saying, okay, this person on the left edge, you're going to sit on the top of the circle, and then we're going to arrange it around counterclockwise. Since 2 seating arrangements are considered the same if everyone keeps the same neighbors but has a different position, we know that there are 6 different ways to seat people that produce the same neighbor relations, so we have to divide out by 6. So 6 factorial over 6 is just 5 factorial, which is 120. And in general, if you have the same problem with n people, the answer will be n minus 1 factorial. Now, in general, when you're solving competition problems, you always want to respect the symmetry of the problem. It'll tend to reward you when you respect the problem symmetry. So what you want to do is you want to figure out, well, this symmetry, how does that give me a relationship between the items of the problem? So for here, we have the 6 factorial of just arranging 6 people, but the circular symmetry that the problem has means that the rotations that we can do if we seat people, those rotations it causes us to like almost immediately jump to division in this problem. If we imagine 720 or 6 factorial items and just grouping them into groups of 6, because there's the problem naturally divides up in that way. Okay, so for this problem, consider a club that has n people. What is the number of ways to form an r-person committee from the total of n people? You may know this. This is also known as a combination. N choose r. But if we're thinking about this problem without reference to that, we need to notice that if we form a committee of r people, there's no order in that committee. It's just like a committee is just a collection of people. They don't hold any particular rank in that committee. They're just totally unordered, right? So if we ever want to compute the number of unordered collections of r people from a larger possible space of n people, what we can do is we can do exactly what we did in the last problem. Or actually, rather, exactly what we did in the last problem. A similar computation to what we did in the last problem. So if we're going to start by thinking about the problem as, well, what if the r people are r committees? What if they were actually ordered? And then we'll just divide out the repeats there. So if there's r possible places in this committee, let's say we have first place, second place, third place, where order actually matters and they're all ranked, like committee person 1, committee person 2, and etc. So there's n choices for the first place on the committee. Then there's n minus 1 choices for the second place person on the committee, all the way down to, this is showing up again, n minus r plus 1, which is the same as n minus quantity r minus 1. So you can tell by that there's r factors in this product. So we really did choose r different times. We chose someone r different times. So we chose r people. Now, that's if order matters, but for each for each collection of R people, there's R factorial ways to order them around, right? So for every collection, for every committee of R people, there's R factorial ways to order them around. So if we think about it, the number we want times R factorial is this ordered factor here, n times n minus 1 times n minus 2, and so on. So if we don't want order, we have to divide by R factorial, right? So each unordered committee of R people will correspond to R factorial ordered choices of R people. So we need to divide our count by R factorial to correct for the overcounting, and therefore our answer is n choose R equals this expression, which if you simplify it, we know that there are R factors on top. So really the top is a descending factorial starting with n, and it descends so that there are there's R factors on top. So if there's R factors on top, well, n minus R factorial, that's going to be, that n minus R factorial is what we didn't include in the numerator, basically. And then we still have to divide by R factorial in the bottom, so that's just sitting there in the bottom. So make sure you look at this and understand what this is saying, like how you get each step, because this is a super important concept that occurs just so often in these problems. Now also note the relationship between permutations and combinations. Now these are called combinations. This final expression here, n choose R, it's basically a fraction n over R without the bar in the middle and with parentheses around them. That will always mean the number of ways to choose a committee of R people from n people. It always means that. And the relationship between permutations and combinations, notice the first equation there, the n times n minus 1 all the way to n minus r plus 1, that is NPR. So that's the number of permutations of R people from n possibilities. So they're just off by a factor of R factorial. So again, just to summarize, if we don't care about the order when choosing R items from a set of n, for example, when choosing a committee, we have a combination. The number of ways to choose R items from a set of n items without regard to order is, oh, that was a typo, n choose R, so you should see the symbol there instead of the typo there, pronounced n choose R, and some sources denote this as C of NR or as NCR. That's often used in classrooms, I think. And there's that formula again from the last slide. This is a really important formula because you're actually going to have to use this formula in this class to do some proofs. So if you want to prove some combinatorial identity, you might want to try converting it to this factorial form, because factorials are easy to work with when you're adding and subtracting fractions, things like that. So whenever you have n choose R, you can use either the middle expression there, n factorial over R factorial times n minus R factorial, or you could use the one on the right. Now the one on the right is usually what we use in practice to compute things. You just think about, oh, you take n, and then you take n minus 1, take n minus 2, and just do it until you've written R numbers on the top, and then just do R factorial on the bottom. That's how we always compute it. For example, there's that example below, 11 choose 3, 11 times 10 times 9 over 3 times 2 times 1. That's just using the equation on the right, the expression on the right, sorry. And the expression in the middle is often used in proofs. So if you want to prove something, you might want to write down the combination in terms of factorials. And if you want to compute a combination, you'll write the combination as that descending factorial that stops after a while over a factorial, like like is demonstrated here. All right, take some time now to work a little bit on these two homework problems. This involves combinations, so I'll give you about 9.5 minutes to work on this, and then we'll move on to more things. Okay, so I want to I want to see how you do with some probability. So go ahead and try these problems, and on the next slides, try those problems when they come up. Um, just try them, and then tomorrow in the video, we'll talk a little bit about how to do these problems. Now, if you've made it this far, this is the last slide. Um, these are a few challenge problems. Um, you may use the binomial theorem if you know it, and no problem if you can't solve them quite yet. We'll talk about the binomial theorem eventually, but this is a collection of some problems that are a little bit harder. For the first one, to prove that, again, you'll want to use the factorial version of combinations, and that one can be done without the binomial theorem, but you might need the binomial theorem to do 24 and 25 and 26. So good luck with those.